All right, here's the video for pages 30 to 41 in your calculator review books, numbers 76 to 92. The graph of f prime, the derivative of f is shown on what intervals is f increasing. F is increasing when f prime is positive, so you could make a number line. I'm not going to do that. I'm just going to look to see where this graph is above the x-axis. So it looks like it's above from -2 to 3, and there's your answer. So if you wanted to make a number line, you would pretty much do the same thing, except at 3, your sign's changing. This is a very easy question. All right, number 77, another very easy question. The figure above shows the graph of a function f with domain 0 to 4. Which of the following statements are true? The limit as x approaches 2 from the left exists. Well, I'm actually going to use this. So from the left, I only care about what's happening as I get close to 2 from the left. I am getting closer and closer to some y value, so this is true. From the right, I only care about what's happening from the right, so I look from the right, and I am getting closer and closer to a single y value from the right. Okay, so that limit exists. But then if I open up both shutters, if I kind of open up both shutters here and look, I don't care about what's happening at the value, but I am not meeting up at the same point, so the limit as x approaches 2 overall does not exist. 1 and 2 only is the answer. Another very easy question. All right, number 78. The first derivative of the function f is defined by f prime of x is equal to sine of x cubed minus x. On one intervals is f increasing again. F increasing means f prime is positive. This is the graphing calculator section. I can get a graph of that guy and take a look to see where this function is positive. It's almost like number 76, except you got to get the graph yourself. So y equals, clear this out, sine of x cubed minus x, and I'm doing it wrong, so don't do what I'm doing, minus x. And I want to go from 0 to 2, so I want to change my window from 0 to 2. And I'm also going to make my y min and max -1 to 1, because sine only goes from -1 to 1. Here's my graph. So here's the graph of what we have going on. Didn't mean to skip you it, but that's okay. So I'm increasing from, say, here to here, because this is f prime. So I want to see where f prime is positive. Or if you're drawing a number line at home, you can go negative here, because we're looking for where the function is above or below the x-axis. Positive, 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 negative there. So f prime is positive, so that means f is doing its increase from wherever this is to wherever that is. Now to find that on the calculator, a few ways. I like this way the best. I go to y, and I'll plug in 0 for y2. That's the x-axis. And I'll go second trace 5. That's the intersect. First curve, I press enter. Second curve, I press enter. And my guess is actually 1. So I know my beginning interval has to begin with a 1, so these are gone. And then I just have to find that other point. So second trace 5, enter, enter, and I can go out to, like, say 1.7. I'll guess it's like 1.7. And it's 1.6905 or 6. So there's my answer. And that's it. All right, 79. If the integral from -5 to 2 of f of x dx is -17, and the integral from 5 to 2 of f of x is -4, what is the value of the integral from -5 to 5? Well, I know my integral. I want to make a little number line for this. My integral from -5 to 2 was -17. And I also know the integral from 5 to 2, which kind of goes backwards, is -4. So I want the integral from 2 to 5. I will make this +4. Okay? So now I know the overall integral. They're asking for the integral from -5 to 5. My overall integral is -17 plus 4, which is -13. Choice B. Number 80. The derivative of the function f is given by f prime of x equals x squared cosine of x squared. It says how many points of inflection does the graph of f have on the open interval -2 to 2. So f prime of x, I'll type it in. So clear this out. X squared cos of x squared. And I only want to go from -2 to 2. So And here's the other thing. We do have to change our y min and max because we have that x squared term in front. If you think about it, though, cosine only goes from -1 to 1. X squared, if you're on -2 to 2, only goes from 0 to 4. 2 squared is 4, right? So I'll make this -5 to 5, or you play around with it. You can reason it out, or you can play around with it and see what you have going on. So here is the graph that I'm looking at. And I'm just noticing for myself, I don't like the fact that there's so much positive y room. So I want to change that. I want to make the positive y go up to like 2. I happen to think that's a much better picture because you're seeing what's happening better at 0. Anyway, this here is the derivative graph. Okay, this is f prime. I want to make an f prime double prime number line based on this because I'm asking about points of inflection. F double prime is the slope of f prime, or whether or not f prime is increasing or decreasing. So it looks like f prime is decreasing till you get to here. So the slope would be negative. Increasing till you get about here. So those slopes are positive. Decreasing till you get to 0. Increasing till you get around here. And then decreasing till you get here. And then increasing. And you have to really be careful. These little ends do count because they're on that full interval. So how many points of inflection? Well, points of inflection are sign changes on the second derivative number line. So I have 1, 2, 3, 4, 5 of them. Choice E. Number 81. If g of x is the antiderivative for f of x and g of 2 is -7, then g of 4 is. So g of x is the antiderivative. So is the antiderivative, right? So if I took g prime of x, that would actually be equal to f of x. So g of 4, if you think about it, if I want to go back to g of 4, I'm going to be involving some sort of integral. I'm not going to be involving f prime at all. So those are out. So now we'll talk about this. The integral from 2 to 4 of f of t dt, well, since g is an antiderivative, this would be g of 4 minus g of 2. So g of 2 is -7, so this isn't quite g of 4. The integral from 2 to 4 of -7 plus f of t dt, you'd have to take the antiderivative of -7, which is -7t, plus g of t evaluated from 2 to 4. And certainly you could see very easily that's not just going to give you plain old g of 4. Now here's an interesting one. -7 plus the integral from 2 to 4 of f of t dt is -7 plus the antiderivative of f is g. So this is g of t evaluated from 2 to 4. So this is really equal to -7 plus g of 4 minus g of 2. But they just told us g of 2 is -7. So this is -7 plus g of 4 minus -7. So minus -7 is +7, and these cancel. So this is in fact g of 4. Another way to look at this is think of f as velocity. Okay. So let's say f is in miles per hour or something. -7 is a position because it's a g value. So this is like the position at 2 plus the integral from 2 to 4 of the velocity, miles per hour, times dt, which is in hours, would give us miles. This is the change in position from 2 to 4. And that would give you the position at 4. Another way to think about it is, if you have -7's tough, but if this was a positive number, like you have 5,000 barrels, 5,000 gallons of oil, plus this integral gives you the change in oil from 2 to 4. Another way to think about it. It's kind of the same idea of the fundamental theorem of calculus, just manipulating it, that we've been using. Number 82 says, particle moves along a straight line with velocity given by v of t as that, which is, I believe, t squared. What is the acceleration at t equals 3? Could not be an easier question on the test. You go to your calculator. You go math 8 because we want the derivative, d dx. You type this thing in. You go 7 minus parentheses 1.01 caret to the negative t squared or negative x squared on the at x equals 3, and you have your answer. 0.0545, just 0.055. Another very easy question. This has been a very easy calculator section so far. All right, 83. What is the area enclosed by these two curves? This one was tricky because what you had to realize was these two curves intersect at three different spots, which means that two different regions are being enclosed. So we clear this out. I'm going to type in the x cubed minus 8x squared plus 18x minus 5 in the y1 bay, and in the y2 bay I'll type in x plus 5. And then we're going to see, I'm actually going to do this bigger. We're going to see, I'm going to do zoom standard at the moment. And we're going to see our graphing calculator. There's the cubic, and there is the line, which actually encompasses, if you see, we have two regions, so I want to pull this out and take a look. So we have the two regions. One here where the parabola is above the line, and then one here where the parabola is below the line. So first things first, we have to kind of figure out when that occurs. So I need second trace 5, enter, 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 to give me some intersection points. So the first intersection point's at x equals 1. That's important. Okay, so this intersection point is at 1. Next one, and you might be able to pick these off, but I'm going to do them second trace 5 anyway. Enter, enter. It looks like it's about 3. And it's 2 actually. See? There's my eyes deceiving me. So it's at 2. And then the third intersection point is over here, which looks to be about 5, but I just want to verify that. So second trace 5. Enter, enter. And I'm going to guess 5. And I'm right. So there we go. So now we have this graph, right? So now we have two integrals we have to make because we have two different regions with a different top and a different bottom. Let me just, lock this down. Group this all together. Just make it a little smaller. We're going to have two integrals. We have the blue area, okay, which is the integral from 1 to 2. The top this time is x minus x plus 5, minus the bottom, which is x cubed minus 8x squared plus 18x minus 5 dx. And we have to add the red, plus the integral from 2 to 5 of the x cubed minus 8x squared plus 18x minus 5 minus x minus 5 dx. And here's the advantage of knowing how to use the calculator. I already have these in as y1 and y2. y1 is the x cubed graph. y2 is the x plus 5. So I'm going to go math 9, integral from 1 to 2 of, well, my line was in there second, so I'm going to go vars, y vars, enter, go down to y2, minus vars, y vars, enter, enter, y1 dx. I'll press enter. And then add plus. Ooh, that's not right. So, did I switch that? Oh, you know what? I'm sorry. I should have done this backwards. Here, the cubic is above the line. So, you know what? I'm going to pause this and fix this. All right, so I fixed my integral. Sorry about that. Anyway, what I'm going to do is I'm just going to take the negative of this value that I messed up. All right, there's my first integral. Now I'm going to add on to that math 9, the integral from 2 to 5 of the x plus 5 I put in the calculator on the y2. So, boop, y2 minus vars, y vars, enter, enter, y1 dx, and 11.83333 is our final answer. So here's what we have going on, and B is the answer. All right, so here we go. Number 84, here's the graph of f prime again. The graph of the derivative of the function f is shown in the figure above. The graph has horizontal tangent lines, x equals -1, 1, and 3, at which of the following values does f have a relative maximum? I would draw the number line out for this one. And some of you I know don't need to do this, but I like to do it anyway. So we're below the x-axis till we get to 2, -2 rather. We're above till we get to 1. At 1 we have a derivative of 0, but we continue above till we get to 4. And then we're below after that, till 5. So where shall we have a relative max? Well, we'll have a relative max. Here, f is decreasing because its derivative is negative. Increasing, continues to increase, and we're decreasing. So we will not have a relative max at 1. We will only have it at 4. And we're not on the closed interval. So 4 only is the answer. Number 85, the table above gives values of a function f and its derivative at selected values of x. If f prime is continuous, what is the value of the integral from -4 to -1 of f prime of x dx? So we have this in terms of numbers. So if we want to take the integral of the derivative, we find the antiderivative. But since it's f prime, the antiderivative is just f, the original function, evaluated from -4 to -1. Which is f at -4 minus f at -1. F at -4 is I'm sorry, I'm doing this backward. F of -1 minus f of -4. I'm on my game right now. So f of -1 is -1.5 minus f of -4 is 0.75. And I believe if I'm doing this right, that gives us -2.25. Choice B. Number 86. The table gives selected values of velocity v of t of a particle moving along the x-axis. At time t equals 0, the particle is at the origin. Which of the following could be the graph of the position function? So here again, let's think about what velocity is telling us. Velocity is telling us what direction we're moving in. It's the derivative. So at 0, we have the position function would have a slope of -1, meaning that it's going down. So at 0, this function is going up. No good. At 0, this function is going up. No good. At C, this function seems to be going down, so I'm going to keep that. At D, this function is going up. No good. And so now, just by thinking about the fact that your velocity is negative at one point, we've eliminated 3 choices. This happens a lot in the calculator section. All right, so now between C and E, we have to decide. At 1, our slope is positive. So that happens certainly on the C graph. It does not happen on the E graph. There's my answer. Very easy question. All right, number 87. An object traveling in a straight line has position x of t at time t. If the initial position is x of 0 equals 2, and the velocity of the object is that function, what is the position of the object at time t equals 3? Well, we have our initial position plus, if we take velocity and integrate it from 0 to 3, that gives us the change in position from 0 to 3. Add it onto the 2, and we have our answer. So we would like to do 2 plus integral of, say, from 0 to 3 of the velocity cube root. You do math, 4 cube root 1 plus x squared dx. Going over there, dx. And 6.512 is the answer. Another very easy question. Number 88. The radius of a sphere is decreasing at a rate of 2 centimeters per second. The radius is decreasing at a rate of 2 centimeters per second means dr dt, this is a related rates problem, is 2. This is what we know. At the instant when the radius of the sphere is 3, so this is the when, we know r is 3. What is the rate of change in square centimeters per second of the surface area of the sphere? So we want to find out the rate of change of the surface area, which I want to call ds over dt. It's a derivative. So we know s is 4 pi r squared. This is a very easy related rates problem. We take the derivative on both sides. I'm sorry, I'm doing d over ds. It's been a long day. D over dt. So ds dt is equal to 4 pi times the derivative of r with respect to t, which would be 2r times dr over dt. Clean this up a little bit. ds over dt is 8 pi r dr over dt, and I think we can just basically plug everything in here. I mean, so we know dr dt was 2. We know the radius was 3. 8 pi ds over dt is just 8 times 3 times 2, which is 48 pi. 48 pi. And it's negative because we're decreasing. So technically, if I were to do this really correctly, dr over dt should be negative 2. Makes this negative, makes this negative, makes that negative, makes that negative. Good thing I didn't get scammed there on the answer choice, choice C. All right, number 89, it says the function f is continuous from negative 2 to 2, and f of 2 is equal to f of negative 2 is equal to f of 2, which is 0. So I want to draw that. Notice, they did not say differentiable. So I want to draw a basic graph and then kind of a more complex version of this situation. F of negative 2 and f of 2 are both 0. So here's a basic version, something like this. A more complex version might include, hey, maybe a point of non-differentiability, because that could happen. Maybe something such as this. Okay? And then it says if there is no c value between negative 2 and 2 for which f prime of c is equal to 0, which of the statements must be true? They're saying there is no place where the derivative is 0. If I look at my basic graph has 2 places where the derivative is 0. So I'm killing the basic graph. This is no good. I'm going to look at my more complex graph and see if that'll help us. It says from negative 2 to 2, f prime of k is greater than 0. Well, that's not true. For example, right here, the derivative is less than 0. And for symmetric reasons, b is wrong also. So then part C says, or choice C says, from negative 2 to 2, f prime exists. Well, on my complex graph, it does not exist at 3 places. 3 k values doesn't exist. D says, from negative 2 to 2, f prime of k exists, but f prime is not continuous. Okay. Well, I'm looking at this, and I'm saying to myself, here's f. F prime of k, though, does not exist at the corners. So there are k values for which the derivative does not exist, which is choice E, which you probably reasoned out by listening to my explanation. Number 90, the function f is continuous on the closed interval 2 to 4 and twice differentiable on the open interval 2 to 4. If f prime of 3 is 2, so we know f prime at 3 is 2, so the function's increasing at 2. And f double prime of x is less than 0 on the open interval 2 to 4, which of the following could be table values for f? Since f double prime of x is less than 0, we know the graph is concave down. But we're increasing at 3. So think about a graph that looks increasing and concave down. Increasing concave down looks like the left side of a sad face. So we kind of want a graph that looks like that. So let's take a look. 2, 3, 4, evenly space those out. 2.5, 5, 6.5 would not be as quite evenly spaced. So here's my graph. This seems to do what I want, but we'll go through the choices. B, 2, 3, 4, evenly spaced out. 2.5, 5, and then 7. This also seems to do what I wanted to do. So now we got 2 choices. We have to handle them. C, 2, 3, 4. We had 3, 5, 6.5. Whoops, 3, 5, 6.5. This also seems to do what we wanted to do. D, if we take a look real quick, the intervals of increase are the same. So 2, 3, 4, this is actually linear along this part, right? 3, 5, 7 are evenly spaced, so we get a line. This would not be the answer. And E, we get 2 at 3.5, 4 at 5, and then, sorry, 3 at 5, and then 4 is more spaced out. So our graph's going to look something like that. That's going to be concave up. So I don't like that. Now, this one's a little trickier. We're down to 3 choices here, but we do get rid of 2. Now, f prime at 3 was 2. Okay? If f prime at 3 was 2, that means the slope at 3 was 2. But if I take a slope, say, from 2 to 3, okay, the change in x is 1 here. The change in y is 2.5. If I take the slope, change in y over change in x on that interval was 2.5 over 1, which is 2.5. But if the function's concave down, that means my rates of change have to be going down, not up. So, from the 2. So this rate of change is too high because as I get past 2, my rate of change should be decreasing. So now this is out. Let's see it. Let's take a look here. From 2 to 3, I'm also increasing by 2.5. That's higher than the derivative. No good. C, if we look from 3 to 5, I'm increasing exactly 2. So I'm not totally going against the notion that f double prime of x is less than 0. And then my decrease keeps lessening. Oh, sorry, my increase keeps lessening as we go along. That one's definitely a tricky question, but choice C is the answer. I'm sorry, guys. You know what? I'm going to redo this question. I was misreading. In my mind, I had f prime of 2 equal to 3. Sorry, I'm going to redo the whole thing here. My apologies. I don't know what was going on in my head. Sorry. Anyway, at any rate, we know f prime of 3 was 2, and f double prime of x is less than 0. So we know we're concave down. That still eliminates D, and it still eliminates E. Okay? Now we're down to A, B, and C. F prime of 3 is 2. So if I kind of made a little graph here, okay, of these functions, which I had before, but I wanted to erase it. So we had 2, 3, 4, 2.5, 5, and then 6.5. Okay? Versus 2, 3, 4, 2.5, 5, and 7. And then 3, 5, and 6.5. So I have that graph still. So here's my other graph. Okay? It's concaving down, but pretty slowly, this guy. This guy is concaving down also. All right. Now my slope at 3 is 2. Okay? So as I go along, my slopes have to be decreasing along the curve. So if I took the slope from, say, 2 to 3, that's a change in y of 2.5 and a change of x is 1. So this is my slope. Then I look from 5 to 6.5. My slope is 1.5. So that is decreasing, 2.5, then the slope was 2, then the slope was 1.5. So this seems eligible to be the answer. B, if I look at my slopes, 2.5, and by the way, I'm just doing the change in f because these intervals of x are just 1. So my slope is 2.5, but then from 5 to 7, it's 2. My tangent line has to ride above the curve. So my slope can't be 2 from 5 to 7. It has to be less than 2. That's the idea of concavity. That the concavity, my slope has to be decreasing as I go along the curve. So this would be out. And then C, my slope from 3 to 5 is 2. Well, the tangent line slope is 2. The tangent line slope has to be less steep than the secant line slope from 2 to 3 because the slopes as I go along are decreasing. So C is out, so A is the answer. I'm sorry about misreading that question. All right, number 91, another very easy one. What is the average value of y equals that function on the closed interval -1 to 3? This is the well, it's 1 over 3 minus -1, the integral from -3 to 1 of y dx. You know, the fraction y. So what do we have here? Clear this out. We have Well, 1 over 3 minus negative 1 is 1/4. I'll put 1 over 4 in here. Math 9. Integral from negative 3 to 1 of, I'll put the alpha y equals enter, cos x over x squared plus x plus 2 dx, and out pops the answer of 0.173, which is not there. That's because I did negative 3 to 1. It should be negative 1 to 3. I guess I'm just tired. Sorry about that, folks. Let's go back up and I'll edit this. Negative 1. Negative 1 to 3. That's what gets us in trouble, this kind of stuff. And that's better. So this is not good. And this is better. 0.1829 or 0.183. Last but not least, number 92. A city located beside a river has a rectangular boundary, as shown in the figure above. The population density of the city at any point along strip x miles from the river's edge is f of x persons per square mile. So this is persons or people per mile squared. And it says, which of the following expressions give the population of the city? This is kind of an awkward question. What I would like to do is look at the units of the things that we have. So x is a distance in miles. So dx is a little change in miles. So dx in all of these integrals is miles. And this is where the units really come in handy, because they take this situation, which is clearly something that's a little strange, and they make this palatable for us. F of x is in people per mile squared. So the integral in a, if I did people per mile squared times miles, that would cancel only 1 miles out, and I get people per mile. That's not the population of the city. We don't measure. We don't say, okay, Rybrook has a population of 5,000 people per mile. B, the 7 is clearly in miles. That's coming from here. So that's miles times people per mile squared times miles. That gets us down to people. So this we're going to keep in the game here. The 28 is coming from 7 times 4. Well, that would be miles times miles. That's miles squared. So I have miles squared times f of x, which is in people per mile squared, times miles. Well, the miles squared cancels, but then I have people miles. We don't measure population in people miles either. Integral from 0 to 7 of f of x dx. Well, this is just as bad as A, because f of x is in people per mile squared times miles. Doesn't have the right units. E, we have our 4, which is in miles, our 0 to 7, or sorry, our f of x, which is people per mile squared times miles. So this is looking like something that could possibly be valid as well. Now the instance is, well, what do we do? Well, x miles from the river's edge is this distance here. So we want to be integrating everything with respect to x. So if you think about it, I'd want to be integrating from, say, 0 to 4. Okay? Because that's what's going on the x-axis. And all of my integrals are written in terms of x. So I want to be integrating from 0 to 4. And then multiplying that by 7 will give us this whole box. So I want to integrate from 0 to 4, because that's what's going on. That's my variable of integration, is from 0 to 4. So I choose choice B. That one is tricky, and I don't think that's something that's totally representative of what we do in this course. But the units really, really help with that one. All right, and that's it.